Hey, hello
Hey,
guys, hello everyone. We are group number 134, and this is our problem statement that we have selected, where we are doing the anomaly detection using, CT and MRI imaging. So this is our notebook, and there are multiple cells. I have all of my colleagues, like we are 5-member team, and we have worked on this. So we each of us will speak about the work done by an individuals. I'll just quickly run through this notebook, and you can see that. And we will start with our parts. Yeah. So as you can see, and yes, okay. So jumping to my point. So yes, my name is Dilip Shukla, and I have developed image pre-processing module that handles CT and MRI images normalization. As you know, there are different technologies. Speaking about the challenging part, they are CT scan and MRIs. They have completely different intensity range. Different physics. They use X-ray and versus proton relaxation. So, we have I've implemented a min-max approach where normalization, where modality rather than forcing them to match, so preserving their unique identities, and then prepare them for the uh, model preparation. So my point was part was the pre-processing and normalization. As you can see the cell, and on the application would be I would love to deploy it to our hospital use case, where to perform a data cleaning, and data normalization for the health records related data. So yes, moving on to Saurav, stage is
hey,
yours. Yes.
thanks, Dilip. Can we go to the section 5 where there
Section
is
5.
augmentation code?
Yes,
Yeah,
yes.
thank you very much, Dilip. Thank you everyone for giving me the opportunity to present this. Well, I built the data augmentator that maintains anatomical correspondence during the augmentation. And the biggest challenge I faced was pairing the CT and MRI images. They must stay aligned during the spatial transforms, but they need different intensity augmentations. So my solutions was with the synchronization of geometric transforms using saved random states like rotation, translation, and elastic deformation from both the modalities, while applying the independent Gaussian noise and gamma correction, right? So if you see the how the augmentation pipeline comes in, if you see the augmentation pair method there, you will see that I have the random state apply rotation to CT, then the reset to the exact same state before rotating MRI. The same deal with translation and elastic deformation. They get exact same geometric transforms. But the key part for this is like the Gaussian noise and the gamma correction. I apply those independently because the noise characteristics are completely different between the two modalities. Once the X-rays are measuring, right, the other measuring magnetic resonance. So this is a dual approach. The synchronized spatial transforms with independent intensity augmentation is what enables the cross-modal consistency detection to work properly. And the real-world example, I would say, is it'll expand our limited annotated medical imaging data sets at our diagnostic centers, improving model generation. So this was a real challenge and the real world example that I would implement it to. I would give it to Aditya to speak on his section. Thank you very much.
Thank you.
All right. Hey everyone, Aditya here. So I had helped design and implement the three reconstruction models, the CNN autoencoder, the VAE, and the video transformer. So the toughest part, on this end was making the VAE sampling operation differentiable for backpropagation. And the way that we solved it is by using the reparameterization trick. What that entails is that like we use the computing mean vector and the log variance vector, then sampling epsilon from standard normal and scaling it. Also, when implementing this, another like an interesting issue that we had was that um, the the losses would just disappear. Like we were just getting NANs all over because the log value, right? That would go like that will scale up so high. So how exactly we fix that is by adding the cable divergence regularization. So it starts, so it's like initially it was like a really high value, but thanks to the divergence regularization, like we were able to start with, let's say some value around thousands, and then, immediately bring it back to, probable values that does not go to nans anymore. Um, so how exactly like is this approach, right, of having multiple reconstruction models, in a usual organization application? Uh, so some of these models might be more sensitive than others. So in application like anomaly or quality control, taking an average across the different models would more likely give you, the more probable or more proper or correct anomaly detection. So yeah, that's basically it. Moving on to Sophia.
So, hi everyone, my name is Sophia Sadaf, and I implemented the vision transformer architecture for anomaly detection. So, let me dive into the transformer architecture because it's quite different from the CNNs. So, if we look at section 9, wherein we are kind of breaking a 256 cross 256 image into 16 cross 16 patches. So that gives us 256 patches in total. The patch extractor here pulls those out, and then patch encoder adds the positional embeddings, because transformers don't inherently know where things are spatially placed. Then we have got these multi-head attention blocks, four heads in our case. And what's cool about is that every patch can attend to every other patch. So unlike CNNs with their limited receptive fields, transformers can capture relationships between distant brain regions into a single layer. Like if there is an anomaly affecting multiple areas, the attention mechanism can pick up on those long ranges connections, and we finish with global average, like pooling to get our 128 dimensional representation, and that feeds into the anomaly detectors. So from here, I pass it on again to Dilip.
Yeah, hi. So I am speaking on behalf of
Debashish here.
our one of the colleagues, Devashish Rawat, who couldn't be with us due to some urgency, some medical emergency. Here I have, so I'm just sharing what is his part. So going to section 12, autoencoders. So Devashish has developed auto encoders, anomaly detection strategies, and including the novel cross-modal consistency detector, as you can see. The hardest challenge that he describes is leveraging differences between CT and MRI to detect anomalies that appear only in one modality. His approach has been he computed both Euclidean and cosine distances between CT and MRI latent features and lesions visible in one modality, but the other could create distance spikes. And this was the challenge that he could solve. The implementation, what he suggests is in the practice that is a cross-modal detection system. What it would be integrated into diagnostic AI pipelines, so as to missing the findings and utilizing what is best in which data type, data set, and making use of the strengths and weaknesses of strengths of each, and having it better, and basically improving the better outcomes. So that's all that he has to say, and that's all we have to say. Thank you. I will stop the recording and will share. So one cell that I have to add is the group cell, including everyone, Dalip, Saurabh, Sophia, Aditya, and Devashish. Yeah, so each ID I will add it, and will share this final one to upload it to our portal. Thank you. I'm stopping the recording.